Hi, my name is Nathan Dvorak. I'm a postdoctoral scholar working in Nufab, and today I will be the opener for the headliner Circon. I will be introducing the new to us, Joel 4700 Fib SEM combo multi-beam system, and then Circon will take it away with drawing some CAD files using scripting for micro and nanofabrication. So this is going to be a very just um, I say a matter of fact type of talk, which is just we finally installed the Joel 4700 into the clean room. It has its own dedicated space that is just for fibbing and SEM imaging. And it's nice, it's quiet, so people can get high resolution images. This system itself is a high resolution SEM, which has a focused ion beam installed in the column. So you can do in situ ion milling and SEM imaging. This is a Schottky field emission system, so it has a stable high current emission. And for Nufab, we are allowing pieces and wafers up to 4 inches into this tool with some heavy caveats because the sample holders that the tool recognizes do not extend past 32 millimeters. So if you go to tilt a 4-inch wafer, just because it fits through the load lock, you could potentially slam it into the detectors, the source, or the ion beam aperture or the electron beam aperture. The ion beam itself is actually a gallium metal source, and we will be having installed soon a Oxford energy EDS system, or an energy dispersive X-ray spectroscopy system. And I'll go through each of these different columns quickly. The first up is we have the 5 detectors that are available. The first is the lower electron detector, which is an Everhart-Thornley detector. This detector is nifty because it can image both electrons and gallium ions. So that's where that in situ simultaneous fibbing and electron imaging happens. There's also the upper electron detector, as Joel calls it, or for some other people, they call it the in-lens detector. This detector I find it kind of unique because it has the ability to screen, so you can apply a bias to it and filter either secondary or backscattered electrons, or image them both at the same time. So you can do some different kind of techniques to see different compositions of materials. This detector also has an optional, not this detector, this system also has an optional backscattered electron detector, which is inserted between the orifice of the electron column and the sample. And this detector has the ability, it has 2 sensing modes where you can have both halves of the detector running in an additive method so that you can see high contrast between different densities of materials depending on your accelerating voltage. Or if you do them subtractively, then you can do topographical imaging because the electron beam then kind of casts a shadow so you can see how the morphology of a surface is. And then lastly, we have the Oxford Ultimax EDS detector. So the electron optical system it consists of a zinc uh, oxide tungsten cathode with according to the factory, resolution of 1.2 nanometers at 15 kilovolts. We are working to see if we can reach that point yet, but I have a little bit of a demonstration on the right here. Well, just an image of something I fibbed up earlier. We're approaching there slowly. Yeah, it's just we finally got the system online, so contact me more if you want more information. You can focus between 20 and 1,000,000 times, and you can get all the way up just within 1.5 millimeters of the sample surface, or as far as 40 millimeters. So if you have really tall samples, we can't accommodate them. And then you can accelerate between 0 and 5, half to 30 kilovolts, and relatively low 1 picoamp up to 300 nanoamps of current, which is very high in my opinion. You can also bias the sample in the event that you have something delicate like photoresist or polymers or PMAA, things like that, so that the electron decelerates as it's coming towards the surface and you don't burn your sample. Next is the ion optical system. Well, this is for the fib. This fib has the ability to do 4 nanometers of resolution at 30 kilovolts, and you can see between 50 to 300,000 times with a beam current of 1 picoamp to 90 nanoamps. The cool things about this tool is this portion is you can draw arbitrary shapes. You can import bitmaps, circles, squares, trapezoids, lines, and you can essentially, if you can convert it to grayscale with a monochrome bitmap, you can in fact fib it, as I'm showing here in this video. I am actively watching with the SEM while doing it, while using the focus ion beam to etch the Northwestern Wildcat into a gold film. And that was in real time too, by the way. Also, we do have a gas injection system available on this tool, so you can mill or you can deposit materials. This tool, they do provide sources which are carbon, platinum, and tungsten. And it's just like ALD. So we inject a little bit of gas and then you use either the ion beam or the electron beam to turn that precursor into the material you desire. And then finally, this is where I'm going to step out my element a little bit because we're still waiting for this tool to come in and get installed, but we will have an EDS system installed. And this is an Oxford Ultimax. This is a really cool detector because you don't need any liquid nitrogen to run it. It runs at room temperature. It has relatively high resolution. It has a large detector area and a large range of elements you can detect. Along with the software suite that comes with it, you can do individual point analysis or arbitrary shapes. You could draw a star and evaluate what the elemental composition is along the vertices of that star. And then this is where I'll leave you. This is my last image, just a fun little wildcat. And after we ablated off the dielectric, we got a much higher resolution, and I'll turn it over to Serkan.
Now, I'm going to be talking about how you can generate computer-aided design files. I'll refer them as CAD files from now on. And we use these files a lot because we're a micro nanofabrication facility and users often have to draw these things. In general, what I've seen, everybody is using their mouse and the screen and their favorite software to draw these things. But hopefully today I'll convey some tips and tricks so that you can streamline your process a little bit better. Right? We have a number of tools that we use these CAD files exclusively, actually, because there's no other way around it. We have two maskless aligners that can use GDS or DXF files, and you can make micron scale devices down to 1 micron with these things. These are heavily used in the clean room, as I'm sure some of you already use them or know them. And we make all kinds of different devices using these, like from microfluidics to electronic devices, microelectronic devices, and such. A lot of biomedical devices are also being made in this using these tools. The next tool that you need CAD files is our laser cutter, and with this tool you can literally cut anything you want into any shape you want as long as you can draw it, and we can get fairly high resolution with this as well. Around like 20 micron is reasonable, but you can push it down to even more than that with certain specific type of substrates. But in the end, you may need very complicated CAD designs that you cannot, draw it by hand in a reasonable amount of time. So I'm hoping this talk will give you a little bit more ideas to create some new shapes. And finally, we have our EV lithography tool, Rate Voyager. In this one, it accepts GDS files or a little bit enhanced GDS files because electron beam lithography often requires a little bit more parameters than standard GDS files can provide. But basically, this is what we use to make nano-sized structures. So we can make nanoparticles, different shapes, or you can make nano-electronic devices. Gap width here is about like 80 nanometers, for example. So these kind of things often require fine control of your design. All right. Historically, most of our users just use AutoCAD to draw their shapes, which is totally fine, by the way. There's nothing wrong with it. It's just, if it's only something you're interested in, some basic layout of the structure, AutoCAD is totally fine. You can use to create very complicated devices like you see in here. It is free with your university email, so there's that advantage with that. But one downside of AutoCAD is if you need to make a lot of small things in one layout, in one wafer, it will crash. It cannot handle more than I don't know, a few thousands of shapes in there very easily. So your computer will crash, software will crash. You'll have hard time managing the designs. For that purpose, I usually recommend users to use KLayout or GDS files. And this KLayout is an open source software. It's much lightweight than AutoCAD. It will work smoothly in your computer, better than AutoCAD. And there's a little bit of a learning curve to this file, creating GDS files, but it's not too bad, really. I mean, I'm sure most of you are already aware. And this software actually can work with DXF files as well. So you don't necessarily need GDS files with this one. I'm mentioning this because I don't know if you noticed that the ProtoLaser only works with DXF files. So, but KLayout will work just fine with that. All right. Now, GDS, this talk is mainly about GDS files. I'm going to show you a Python package to create some simple shapes and parametric shapes and whatnot. But anything I say can be applicable to any DXF files if you're using an appropriate DXF file package for Python. But it will be related to GDS files. So let me just talk about a little bit in detail about GDS files. So this pattern here I created a while back. So this was a lithography test pattern that each square here has different size shapes and periodicity. So these like an array of circles. I have arrays of lines and with different changing parameters, widths and periodicities and whatnot. And you can imagine how hard this would be if I were to draw everything by hand, and also you need to arrange it in a 4-inch wafer layout. This would take quite a long time. And the beauty of the GDS pattern is that it is a hierarchical building scheme. You have some cells that you use another cell, and that cell you can use another cell. So that way it will be a lot more memory efficient. It's not going to bog your computer. And also our tools, masks, writers, or even tools will handle these file types better than the DXF files if you have this many small stuff in the shape. Right? Okay, so let's keep going. Now, there are some limitations to this file type that you should be aware of, especially if you're willing to create these things with a script. Well, I mean, scripts usually have shortcuts or different ways of creating any complicated shape, but the base file format only has polygons and paths. There's no circle. There are no circles, for example, in the GDS files. You just need to make a polygon with enough number of vertices to create a circle. From afar, they look like a circle, I guess. There's an inherent limit of how many vertices an object can have. This is also true for AutoCAD, by the way, if you're not aware of it. I mean, not the number, but there is a limit in AutoCAD too. So any single object in your file cannot have more than this number of points. But in practical applications, I would limit this number to 600 to 1000 somewhere, because again, it becomes hard for software to handle this many points. Each time you click on an object, there would be a delay before it can highlight the object. So it's easier to limit how many points you keep in one single object. And then with the EBL GDS files, there are additional elements or objects that you might want to draw, like curved elements. They will be interpreted differently in the electron beam column. And there's also single pixel lines and single pixel dots that are not available to the native GDS format. But there are packages that can create these kind of things so that you can prepare everything in advance before you come to the lab. All right, here a little bit of a comparison between GDS and a DXF file. Polygons in the GDS file are polylines in the DXF file. So when you draw a polyline, in AutoCAD, for example, it will be interpreted as a polygon in there. There are paths in GDS files that you can draw some sort of a line with a finite width to it, and the interpreter will understand that. As far as I'm aware, there's no such thing in AutoCAD, but I'm not sure about that. The XF does have circles, which has a little bit, which is a little bit advantages over GDS file, especially if you are just doing optical lithography using the maskless aligner tools, because circles in DXF will look like more circles than circles you can make with GDS files because they're polygons basically. And then there are some additional stuff that you can do with great GDS files that are not available in the DXF. Any circle you draw in the AutoCAD will be converted to a polygon, by the way, if you open it in the KLayout. All right, so this is a little bit of an introduction to the file system. And these are some packages that I found over the years in GitHub. And there are, some heroes of, microfabrication experts and coder geniuses. They create these things. By the way, I just want to give a shout out to them. So you can find all of these things in GitHub, and they are very, very useful things. And they spend countless hours, I think. So it's best we acknowledge them, I guess. So today I'm going to use this GDS TK to demonstrate how you can use it and create some GDS files with it. It's a Python library. It's available on GitHub. You can install it on your computer and just keep using it. This one I recently discovered. Somebody add this other GDS package, the RAID stuff in it, so it can do RAID specific elements in the file. So this is also kind of useful. I often recommend users using this MATLAB library for creating EBL things, and a few of our users used it, and they speak highly about this package too. So you can check that out if you're into EB lithography. And then recently I discovered this GDS factory package. This is kind of an interesting thing because it is capable of auto routing. So especially if you're making like a waveguides and stuff like that, you can put your like entrance port and output port, and then it can route it automatically based on wherever you put your objects. And so yeah, it's worth checking out. I don't have much experience with it, so I cannot talk about it, but it seems really, really promising. And this one, I just put it there. I used to use this one before I switched to GDS-DK. It's easy DXF. It's a very good library for creating DXF files. So again, anything I'm going to show you today is also applicable for DXF files, just as a reminder. All right. So now I'll try to show a few examples, and we'll do a little bit of live coding, and I apologize if things break down. So this is going to be the first device that I'm going to show you. So it's basically a simple two-pole device. We have two contact pads on left and right, and we have the active device region in the middle, which we might want to sweep the length on the width between these two contacts. Right, so it's a very simple thing. But imagine, if you need to make like hundreds of these with different parameters, then it can be really tedious to draw by hand, right? And the next example, we're going to do a hierarchical array. So this is mostly for maybe EBL related, EBL users, because they often do these kind of shapes a lot. Some sort of a nanoparticle, and then we want to make an array of it. And if we have time left, then I want to talk about a little bit more complicated shapes like these. Maybe. All right, so now let's switch to the. All right, so here we go. Now I'm going to use Jupyter Notebook. Just I like using it, and it's very easy to do. But you can use your favorite development environment. These are all Python scripts, Python codes that will work with anything. Obviously, we need to import our library first, so I'm just going to do that. And this is the device that we want to make, right? So you can draw this by hand in KLayout, but the purpose here is that we're going to draw it with the script, right? All right. Now, each file is referred as a library in this package. So we need to create a library that contains all the cells and the shapes we want to make. So that's what this line is going to do. So we're just creating a library, and then we're going to have to create a cell in this library, right? So remember GDS files that I showed you, it has multiple cells. You can refer one cell into another cell and whatnot. So this is what it is going to do. So we just add a cell into this library. All right. Now it's time to add different objects into this cell, right? So I'm defining a left contact pad, which is going to be a rectangle object. You can call it from the GDS library. And here are the parameters of this object. So you need to define the first corner and the second corner, and you can define which layer you want it to go. It's that simple. And this is going to define left contact pad. And then after we define the object, we add it to the cell using this add function of the cell component, all right? And similarly, we're going to do the right contact pad. We're going to do the middle one, and then we're going to the left middle and the right middle one, all right? These names are arbitrary. You can name them whatever you want to name them. And finally, we're going to write everything we've done into the GDS file, which is going to be this two-pole device GDS, all right? So let's take a look at the device. So there it is. We have left contact pad, right contact pad, and two middle contacts, right? And right now we hard coded this. So the if you look at the parameters of this thing, you can see the lower left corner, -75, -25, and upper right corner, 25, -25, which is here in the script, right? So nothing fancy. You could have done this by hand in the software as well, right? Now, but we want to do it parametrically, right? So I'm defining a width and a length for each of them here. And then we're going to create this library from scratch. This is important, by the way. Each time you want to do some changes, you need to create everything from scratch. Otherwise, things will start adding up. All right, so we created, again, the library and the cell. So this time, instead of hard coding this two middle objects, I am using my parameters that I defined here, right? So each time when I change this parameter, for example, then they should change as well. So let's do that real quick. So now I'm going to save this file again, and if we reload it, you should see the shapes are changing a little bit. And now that it is parameterized, we can do whatever we want. So for example, if I wanted to make the width 1 micron, I can just do that. And my file will be automatically updated. And now I have a 1 micron gap in between, all right? Very good. Now let's say we want to make a parameter sweep, okay? Let's say you're creating a layout over a chip or a full wafer. In one axis, I want to sweep one parameter, and the other axis and the length and the other parameter, right? For that, we need to create some list of different widths that we want. And the also nice thing about this is you see I have two 1 micron widths, 2 3 micron widths. So if you want some parameters repeated more than the others, you can do that. This doesn't have to be like a monotonically increasing list. So, it's fine if that's what you need. But often, you want to have multiples of the same structure. So if one device doesn't work, you can use the other device. So it's very good. Then again, we start creating the library and the cell. Now this time, what we need is we need to put all this in a nested for loop. Each loop will do one axis. And the problem is, though, if you just do this in a loop, all the objects will be created in the same spot in the CAD environment, which is not something we want. Each time we create a new device, we need to shift the position of the devices to left or right or up and down for a certain amount, right? This translate function at each object will help us do that. So here what I did was I defined a periodicity that will be the distance between each object in each dimension. You can use different dimensions for X and Y though, but for this one, I just use one. And we're defining an incremental X and Y shift parameters, dx, dy. And this translate command will translate each object by the same amount in the loop. And after each loop ends, we shift our translation by one period. So everything will shift accordingly, right? So let's keep going. So, and we write it. So this must have written multiples of these things in there. Let's see, we reload the file and there we go, right? You see how easy it is? With just a few lines of code, we can make how many? So this is like 6, 7 by something 6. So 42 different devices in just one go, right? Very good. But now this can quickly become, go out of hand because now we just need to follow, okay, which device was what you're under the microscope, you're, trying to measure these things and that. Now you need to know what are these parameters, right? So you cannot always just start counting them from some corner or whatnot. So since we can do scripting, we can add labels to each and every device separate. This is what I'm going to do now. So again, we refresh our library. So this is the original loop that we created earlier here. And here I'm creating labels so that we have a template for label. It's going to embed the width and the length of each device. And we assign the position here in the position command in this GDS-TK text object. Don't worry about this star at the beginning. I mean, if you know how Python works, I'm sure you know what it means, but it's this text command, I mean, this text function generates each text as a separate polygon, and we kind of need to untopple these and just make them separate so that it adds everything to the thing. So it's just a technical thing for Python scripting, but this is going to write the text on top of our device. And in addition to that, what you can do is you can create a serial number or a device number for each and every device, a unique identifier. This is very useful, especially when you have multiple different devices that you need to measure. You can keep track of which device you actually measure, especially if you have the same device in multiple places in your chip, on your chip, right? So this is a serial number template. So it's just going to put a D and write the serial number, right? So let's run this and see what happens. So if you reload it, you can see each device is now having a width, length, and a device identifier, right? Which is very, very cool. But, I don't know about you, but this font is really, really ugly. Plus, when you, if you have some metal liftoff experience, you want to have these fonts ventilated. That's what it's called. So you want to have some openings from inside of this circle or this zero to the outside so that when you do a liftoff, the middle part doesn't stay in there so they look nicer, right? So for that, we need to change the font a little bit, right? And there is a way to do it using generic Matplotlib library functions that you can use any font that is installed on your computer that you can change everything to whatever you want. So let's just load that, refresh the thing. Then, so you see, I'm going to apply Times New Roman to the width and length, and the serial will be this LED.matrix font, and you'll see what what they look like in a second. So let's do that, and here we go, right? So you can use any fonts. Obviously, you don't want to use Times New Roman, for microfabrication. This, I mean, although they look nice, but when you do these things, they will not look as nice, and you are unnecessarily straining your fabrication abilities. And again, these are not ventilated fonts. Instead, you should use something similar to this. You see, inside of this font has connection to the outside world. So when you do liftoff, everything will lift off nicely. You don't necessarily need to use this font. You can use like any kind of stencil fonts. They're also very okay to use. All right. So there it is. By creating how many? So there's like maybe 20, 25 lines of code. You can create any kind of like sweep, like parameter sweep you want. All we have to do is if you want to change something, let's say, where is my list of bits? So let's say I want to do this twice, right? So what I can do is I can just copy this and let's add it to the list. All right, and if I run everything again, here we go. We will have a lot more of these devices in just a few clicks. All right. So you can see how powerful this technique is. All right. Now, the next example. What time is it? All right. I'm going to speed up a little bit. So this is the hierarchical one. So this is again mostly for EPL users, but you can think of different ways of using this even if you're doing optical lithography. In this one, we are going to create a base cell which only contains a single circle. And then we're going to repeat that cell in another cell that will give us this periodic pattern, right? Here is how we start. So this is the, we start the library, we create a base cell with the name base diameter 2 micron. And then we're going to create a circle in there using this ellipse function. We define the center, radius, and layer. This tolerance parameter is important for curved elements. I'm going to explain in a second. So let's bring up the file over here. So there we go. We only have one single cell in this file, and there's a circle. You see how it makes the circle? This is still a polygon with this many number of vertices. If you decrease the tolerance and try again, you'll see the circle will be a lot smoother. So there's more vertices, right? So that's why this tolerance is important. Just wanted to show you, all right? Now, we want to use this cell in another cell that I will call array with a periodicity of 5 micron, right? So that's how we define it. So we create another cell in the file, and we reference to the base cell with these parameters. So we define number of columns, number of rows, and spacing between these circles in X and Y axis, right? Let's do that real quick and reload the file. So you see now we have this hierarchical build. So we have our base cell and we have our array. I just need to show that on top, and here you can see this is my array that is created, just a few lines of code. Let's say I wanted 100 by 100. I can quickly do that by just changing these two numbers. And let's start over. I kind of need to create the base again. And all right, there we go. If we reload it, there we go. So now we have 100 by 100. Very quick. All right. Now, I mean, this much you can actually do manually. It's not really that hard to do using K-layout. But let's say you want different diameters, different periodicities, and different things. In that case, what we want to do is we want to create a function that will generate this thing automatically based on a few parameters that we can define, like diameter, X periodicity, Y periodicity, and rows and column numbers, right? Now, there is one thing that you need to be careful though. That is, you need to check if the name, because we're going to create them automatically, then, I mean, the GDS file does not like to have multiple cells with the same name. So it's going to give you an error. It's not going to work. That's why there is a sanity check here. It's just going to look in the database. There is a same name cell in there. It's not going to create it again. All right. So that's what we need to do. So now, once you have this array, once you have this function created, now we can just call this function over and over again with different parameters that we need, different number of columns, maybe different number of periodicities, or different period lengths, or different diameters. And when you run this and save it, we will have multiple arrays with different parameters. Right? It all depends, and you obviously need to create a template for names of these things and choose something reasonable. But if we look any one of them, you can see there are created. So this one uses this base D2 cell in this configuration, 7 micron periodicity, but this one uses the same base cell, but with a different, more tight impact configuration, right? So it's very easy. Instead of a circle, if you change your base cell now to a triangle or any kind of complicated shape, you can do it with a polygon command. You'll have arrays of that thing, basically, right? All right. Do you have any questions? You can put it in the chat, I suppose, or if you want me to explain something in detail. So, Katie, how are we doing on time?
We have time,
We have,
cover
oh,
if
all
people
right.
have questions, yeah.
Okay. All right. So I'll just keep going then. All right. So now let's do some more fancy stuff, right? So these are some things you can do pretty much manually as well if you have time and don't mind. But as you can see, the script is going to help you a lot to make them streamlined. But some patterns like these serpentine things, or there's some spiral stuff, some complicated patterns, they can be really, really tedious to do by hand. All right. So now let's try to do the serpentine thing first. Now we start with again creating the library and the cell. We need NumPy here because we kind of need to do some sort of trigonometry a little bit down the line. But this time we are going to use the path object, this flex path command or function to generate these traces. And it starts with initializing the path like this. This current point over here is defined as the starting point of this path. And I'm starting at the origin for this example. And I also define a few of parameters that I'm going to need down the line. The trace width will be the width of each of these serpentine patterns. The radius will be the radius of this turn here. And there's pitch that is going to be the distance between each of these half circles, right? So from here to here, for example, the pitch is this distance over here. All right. And so let's start it. Then we need to create the line segment by segment. Basically, we're going to create a straight segment and then the arc and then another straight segment and then the arc and so on and so forth. I define this pitch parameter here as a vector. So you see this is a x10 and y0 at the moment. There's a reason for that because we can put some slope into it if we want to in the end. So right now, but right now it's just horizontal. All right. And then what this does is it is shifting the current point from 0 to 10 or whatever the pitch amount here, right? And then if we call the segment function, it is going to join these 2 points. The original point, which is in the path right now, it's starting point. It will shift it to the 10 micron in this case, right? So it will draw a straight line 10 micron. And then it will add an arc of radius 3 micron at the end of that thing. So let's run it and we bring it up. 17. And there we go. See that? We have we start at 0 and then we go 10 micron to do right, and then we put the arc there. All right. So we need to keep going this way. So let's just uncomment this. So next thing is we need to define where the next segment will end, which is right about here. So this function here is just calculating that. It's adding 2 radius and then it shifts the thing like left 10 micron with this. Then it will add another segment and it will add another arc to this and it will go there. And the arcs are defined, by the way, if you missed it, you just need to define the initial angle and the final angle of the arc. All right, so let's run this again. Just need to start over. All right, if we reload it, there we go. So this is our base unit for our serpentine pattern, right? Very simple. Now, you can do things like changing the radius or maybe increasing the distance between the arcs, and it should just do it right away, right? See, it's a little bit bigger. All right. Now, what we want now is to put everything in a loop again, as we did. So there's the loop parameter here, 5 times. It's going to repeat this 5 times with these settings in this one, with the same pitch that we started with, and it should save it. So this is the loop. So right. So it's going to run this 5 times, and we reload it, and you can see it's like that. All right. All right. Now, there is one thing that I should show you. So you see this is a path object, and if you check the properties, you see it says path properties, and you can actually edit these things using K-layout later. So you see now it's sticker path, but if you change the simple path attribute to false, it is going to create a polygon, which can be useful because if you say this file is a DXF file, you may need to convert it to a polygon to be able to use this properly in laser cutter, right? So just a little bit of a note for that, right? And it's nice that you see it's splitting this polygon automatically into different sections. This is just to keep number of vertices to a minimum, so that if you create a very long serpentine pattern, the number of vertices are not going to exceed the allowable limit. All right, so it's something that can be useful. All right. Now, often when you do electrical devices, a lot of medical like flexible device, our users that make those kind of things need these kind of serpentine patterns, but they need more than one running at the same time, because you need one lead going into your device and then one lead coming out of your device, which is again very easy to do. Instead of defining the path, initializing the path with a single width, if we initialize it with multiple list of widths, basically. So I'm going to use the trace is 1 right now. So this will be 1 micron, 2 micron, and 1 micron. And you can define where everything will go, different layers in a list. And also there's this offset parameter, which is going to be the distance between the paths. And if we run this, it should give us 3 different serpentine patterns. Well, obviously you need to be careful about your parameters. Right now, our radius is too small, so it's kind of like looping back onto itself. So let's increase the radius to maybe 6 and try this one more time. And there we go. All right, very nice and simple that we have triple serpentine lines that are running this way. Now, you can do different. Remember, I told you the pitch is defined as an array. If I, instead of like 10-0, if I do like 10-3, you can have it tilted this way too, if it is something you need. But you need to be careful when you do this, because you see what happens here. You need to kind of calculate the starting and the ending of these curves using a bit of trigonometry. And also you might want to do some if one curve is going this way, the other one may need to go the other way or something like that. But you can make it much nicer if you, I'm not going to go through the details of this one, but just, I'm sure you're capable of understanding trigonometric functions, but it will create much nicer looking serpentines. And, if you need longer delay lines, or maybe you're creating a resistor to heat up some certain section and you need more length in your lines, metal lines, then you can cram more things together without them touching anywhere. All right. Okay. This is my final example. It's a spiral device, and it is a Archimedes spiral. It's just defined, the radius is defined by some constant times the angle, and so in this one, we're basically going to create a segment bit by bit by running the angle over 2 pi full circle. At the same time, we are going to reduce the radius. That way it will revolve onto itself, right? And this is how you can calculate the each point coordinates by using from polar coordinates to Cartesian coordinates. And we open this real quick. And all right, so if we run this, it should create something. Where is my spiral? There it is. All right, so there it is. So now you can again define different. So let's say I don't want it to be this big. I can change it and reload it so it be a smaller spiral. It starts from the outside, by the way, it goes all the way inward. All right. And let's see, again, I'm initializing the path from a point that is 1 radius away from here. Then in the loop, we are finding the next point. And after we create the segment, we reduce the radius by this amount here, 1 micron each tick, and the angle is also reduced. And the angle increment is defined in its pi over 100, right? So each time it does that, and you can see it's creating multiple segments. It goes all around the device, right? And again, if you do a little bit of mathematics and whatnot, you can create things like these double spirals and whatnot. You know, it can be quite complicated. Fine. There we go. And so this one is starting from here, going all the way in, jumping from one end and start going revolving outside. So it's not, you know, without getting short, it goes all the way in and then it comes all the way out again, right? So we can make things a lot more complicated. The reason why I want to show you this is, you see, this bit of code created multiple paths which are separated because of that limit that I told you in the beginning of the slides. Because, you know, if you have too many points in one path, you know, when you click on it, the software bogs down and just gets slowed down. It can be too much for the computer to handle. That's why I'm capping it at 600 points. So each time it creates a path with 600 points, it stops, start a new one, and just keep going that way. Right? That's something you need to be you need to think about. Again, if you instead of doing it the simple path function over here, if you make it false, it will create a polygon, and then you actually don't need to worry about this because it's, you know, whoever created the package, they were smart enough to include that thing that it splits the thing automatically, so you don't have to worry about that. All right, so that's all my examples. And if you have any more questions, I'm happy to answer them. And here are our contact information. Unfortunately, I don't have a GitHub account, so I cannot put this code in there to share with you. But if you send me an email, I'm happy to share the notebook with you. And you can experiment yourself with creating different things and build up on that. Okay.